Alexander Fleming, a Scottish researcher, is credited with the discovery of penicillin in 1928, but the first antibiotic was actually discovered by accident. It was often said that Fleming was a careless technician. While experimenting with the influenza virus in London, he returned from a 2-week-long vacation back to the laboratory. Fleming returned to find that mold had developed on an accidentally contaminated Staphylococcus culture plate. Upon examination of the mold, he noticed that the culture prevented the growth of staphylococci. Fleming continued to test and do experiments to understand why the new mold had stopped the growth of Staphylococcus. It turned out that the mold was releasing a compound that could kill bacteria in an attempt to have more space to grow and more nutrients to itself. In an article, Fleming described the colony as a fluffy white mass which rapidly increased in size and after a few days sporulates and changes color from dark green to black to bright yellow. Fleming also said, "One sometimes finds what one is not looking for. When I woke up at dawn at September 28, 1928, I certainly didn't plan to revolutionize all medicine by discovering the world's first antibiotic or bacteria killer, but I guess that's exactly what I did." Though penicillin would eventually be used to cure everything from blood poisoning, from minor injuries to pneumonia to rheumatic fever, Fleming's 1929 published study focused mainly on the antibiotic's possible utility for bacteriologists. Penicillin made a difference during the first half of the 20th century. The first patient was successfully treated for Staphylococcus septima in the United States in 1942. However, supply was limited and demand was high in the early days of penicillin. Penicillin helped reduce the number of deaths and amputations of troops during World War II. According to records, there were only 400 million units of penicillin available during the first 5 months of 1943. By the time World War II ended, U.S. companies were making 650 billion units a month.
So what we have here is the basic structure of a molecule of penicillin. It consists of 16 carbons, 18 hydrogens, 2 nitrogens, and 1 sulfur. The R on the left of the molecule represents the side chain that differentiates distinct penicillins from one another. The group being boxed right now is in an acyl group, which is essentially responsible for killing gram-negative bacteria that contains an additional outer membrane. The beta-lactam ring, however, kills off gram-positive bacteria due to its specific structure that we will look at more closely in just a moment. Fused to the right of the beta-lactam ring is a 5-membered ring known as the thiazolidine ring, which helps support the reactiveness of the beta-lactam ring. The beta-lactam ring consists of an amide functional group, a double-bonded oxygen, and 3 carbons. This ring is the main component of penicillin that is responsible for killing gram-positive bacteria. As shown here, the rings appear to be in the formation of a square. However, the hybridization of the carbons differ from one another. The top 2 carbons have an sp3 hybridization, while the bottom carbon has a hybridization of sp2. This causes an imbalance between the angles that form and puts a lot of tension on the ring. Eventually, the bond between the bottom carbon and the nitrogen breaks, and it is this broken bond that then supports penicillin's antibacterial activity. Now, penicillin is considered an irreversible enzyme inhibitor, which essentially means that it is a molecule that binds to an enzyme and limits or stops its activity. If we consider a gram-positive bacterial cell, there is a cell membrane that protects the inside. What is referred to as the building block of this membrane is known as peptidoglycan. Peptidoglycan is a polymer consisting of sugars and amino acids that not only provides a strong structure for the outside of the bacterial cell, but assists in binary fission, which is how bacteria reproduce. In order for bacteria to multiply, the cell membrane is continuously broken and therefore needs to be repaired. This is where the enzyme DD transpeptidase comes into play. DD transpeptidase cross-links the peptidoglycan so that there are no longer any holes or breaks in the cell membrane. Therefore, the beta-lactam ring, which now contains an unbonded carbon, attaches to the DD transpeptidase enzyme that it inhibits, destroying the makeup of the bacteria's cell membrane. This eases the tension within the ring and gives the nitrogen a negative formal charge. The bacteria cell, however, cannot repair its membrane without the assistance of the DD transpeptidase and begins to flood. Eventually, the cell bursts and penicillin successfully kills the gram-positive bacteria.
Penicillin